Go. And look at that, it barely wants to get going. I'm getting nervous that it might not even move. I did notice I got my string rubbing a little bit, so I hope that's just a small error and that we'll see in the data, but it won't throw off our answer. And stop. And so sure enough, more time here. And so we're at 2349. So 2349. All right, move it out again. Looks like 3 more to do. And so the 15 now becomes 18. So now it's 18 centimeters out. And we'll wind this up. Maybe a little more right there. The stopwatch close by. Whoops. And so here is my 80. Okay. Reset. 1, 2, 3, go. And so there it unwinds. Taking more and more time. Smaller and smaller angular acceleration. Because more and more inertia. Which conceptually, you're seeing that moving the weights out does give it more inertia. Stop. And so again, inertia is not just the amount of mass, it's also where they're located. And that's what makes rotation a little bit harder. And this is that hard one. So that's why this was part of the lab. So I could keep saying that and you could actually see it yourself. All right, 2 more here. And so let's move this out to 21. And this one out to 21. And let's wind it up. And let's adjust it so that it is 80 centimeters above the ground. Take the stopwatch and ready, start. Much slower. And so now I think we're convinced for sure that it's much slower. Now the question is it slower by, this proportional to the square? Stop. And so I got a 2912. And so 2912. And one more, hopefully the most inertia of all. And the farthest we can move them out on our little apparatus here. Move them to 24 and wind it up. Put that weight on here. Grab the meter stick here and adjust it to 80. Hold it there. And ready, go. Wow. Good. It's going. Barely. But it's going. And so this one, hopefully, is going to be more than that 29 we got before. Sure looks like it's going to be. And so as it unwinds, we get down here to the bottom and stop. And so 3217. And so our last piece of data for part 1 is 3217. Oh, there's a crazy monitor in the way here. Can't quite see that. No. Does this thing move, bend, dip, fall? Okay. So there's the last piece of data. And so I'll say it again. Your job here is to go ahead and use the first equation and the second equation and the fourth equation and have this chart. Because once you have that, you're asked to make 2 plots. Let's see. The first plot is on page 42. And it says plot the moment of inertia versus little r. And so that's these 2 columns. And you will hopefully see something that looks a little bit like this. Because the fact that it, 0 radius, well, I guess you didn't measure anything at 0 radius, so I shouldn't have put one there. But the smallest one we measured is 3 centimeters. And if you had moved them all the way in, there would be some moment of inertia. And so it should be following a pattern that's, not 0 when you move them all the way in. But they keep getting bigger, and my whole point was to get you to see what I told you in the lecture. That is, the moment of inertia can be thought of as the sum of the mi and the di squared. In this case, we're writing the d as an r squared. Whereas in class, we wrote it as a d. And I told you that we were going to come into the lab and use our measurements in the lab to show that it follows an r squared pattern. And this would show it because we know that a r squared pattern is the shape of a parabola. And that sure looks like a parabola. Which is why then the next graph that you do, page 43, will say go ahead and plot the inertia versus the square of the radius. Which is why you will need these numbers here, the square of them. And this is the one where hopefully then you will see a straight line. And it's been a while since we've done graphs and straight lines, but remember the straight line says the vertical axis is proportional then to the horizontal axis. And so it follows an r squared pattern. So that's your proof. Anytime you see a straight line, this right here would be equal to something, which in a math class we would call it the slope of this line, times whatever you're plotting over here, which would be r squared. And so that's why lines were so useful for us. Now in this one, there would be plus what in a math class you would call an intercept. That would really just be, when all the weights were on top of each other, or the 2 square weights were on top of each other, because we still have the base that is spread out. And so this is the equation of a line. But it's our proof to say that as you move the weights out, they follow this r squared pattern. And so that's really the point of this. Now, let's go on to part 2. And so I guess over here I will put part 2. And part 2 is a little bit easier than part 1. Part 1, as I said, was hopefully giving you an experiment that would help you try to get an understanding of rotational inertia a little bit better. I think that's the hardest, or one of the hardest of this chapter 8. And part 2 is about the torque. And as you heard me in the lecture, the torque is this R alpha. Now, in our case, we're using capital R for the torque radius, not to be confused with the little r. But I was trying to point out in class that the other hard thing about rotation is that torque is more than force. Torque is a force and a lever arm. The lever arm is just as important as the amount of force. So to get something to rotate, it depends not only how much force, but also what that lever arm is. And so that's why we have this part 2, is to show you that the lever arm does matter. Most people, have no troubles believing that if you gave it more force, it would then rotate faster. They get that. But it's that extra distance, that extra lever arm that is kind of important here. So, looking at your table here, you are going to do kind of the same thing, but on a smaller scale. And so let's measure the height in centimeters together. And again, I'll probably just, I don't know if I can get 80 every time because the string will wrap too much. So I'm going to leave that alone. I'll try to get 80. Let's see what happens. But let me also then put, so centimeters, T for time in seconds. So those are the two I'm going to measure. We're only going to do it 3 times. Okay, 1, 2, 3. And of course, we will get the acceleration of that little weight dropping down. And I should call that its translational acceleration. But if you divide that by its torque radius, so again, same 2 equations, this you get by equation 1, this you get by equation 2, you will get the angular acceleration. And of course, what's going to change is the torque radius. Okay? And our torque radius is going to go from a small, a medium, and a big, which, by the way, I would say I've already done the big one. The big one, right, that's what this one was. And the bigger torque radius of 1.88 I've been doing already. Let's measure the other torque radius, or radii, before we collect any data here. And since I already have the string kind of wrapped up on the bigger one, I'll go to the medium one here. Okay, so this says 25.25. Now let me grab my calculator and say it again. 25.25 is actually the diameter, and that's also in millimeters. So I'll first divide that by 10 to get centimeters, then I'll divide that by 2 to get the torque radius. So the medium one has a torque radius of 1.26 centimeters. And let's do the small one. Make that measurement before we actually measure anything here. And so the smaller one, right here, looks like a 16.92. All right, same idea. Oh, I bumped this. It's still on. So 16.92 divided by 10, and then that answer divided by 2 gives me the small torque radius of 0.85, and I'll just do 2 decimals there. All right, so I'm going to be changing the torque by changing the torque radius. That's the thing to notice. I will always be hanging the same amount of mass. And what you're going to hopefully see is that this acceleration does change. That is, over here it has a big acceleration, and here it has a small, and here it's a medium. Because this is illustrating that the torque changes with the torque radius. Even though I'm not going to change the weight, the force. That's the idea. Now I need to come to the instructions, because the instructions say, now place those little weights at a set position and don't move them. All right, and they say place them at a distance of 12. All right, so let me come over here. and put this at 12. Let me take that one off and put this one also at 12. Okay, and let me wrap up the string and get height and time for each of those cases. Now, I'll save a little bit of effort here because for the 12 I've already done, right? There's a 12. When it was on the big radius, it was 80 centimeters and it was 21.15. So I'm just going to transfer that over here. So 21.15 for the time for 80 centimeters when they were a distance of 12 out. And then this number here, I haven't calculated yet, but you probably have by this point. You could also then just transfer the translation, where is it, right here, the translational acceleration and then the angular acceleration. So let me not do that one again, but let's do the other two that we haven't done. I'll go to the medium one first here. So let me grab the stopwatch, which I left over here, and let me turn it back on and reset it. Let me take this string, and looks like it's hitting the ground already. So if I just leave the extra part of the string on the big pulley, the rest of this, and let me pull a little bit off just to make sure. Okay, so I'm just going to take the rest of this string because I won't really be using that longer string, and I'm just going to wrap it around, and that way I won't have too much string on that medium pulley. I think that'll allow me to get up here to 80 just fine. That's what I was saying earlier. I was kind of concerned about wrapping all that string on a small pulley, but that was kind of my answer to that. Okay, so then if I grab then this meter stick, and adjust it. So start at 80 and say 1, 2, 3, go. You might see how sluggish it is, right? And I would say in this case it's sluggish because we're not getting as much torque as before. See, before we had it on the bigger pulley, and the torque depends not just on the weight, it's the same weight as before, but also on that torque radius or the lever arm. And so that's why it's so sluggish here. All right, well, we're getting close, and so as it comes down and stop. All right, so I got a time of 32.75 for a height of 80. And so again, you can just see in the numbers, the time is bigger here, so the acceleration is going to be smaller. That, again, my way of saying that, look, that's because it's less torque, and it's less torque because it's less of a torque radius. It's less of a lever arm. It's not less force, it's less torque. And torque is more than force. It also includes the lever arm. All right, and then so the last one here we'll do together, and then we'll maybe talk a little bit about the other graph and be done. Let's wind it up. Then, on that smallest of the torque radii, so I'm going to wind it up on this small pulley, and hopefully we'll kind of see the same effect, that the torque is going to be less, not because we're giving it less force, but a smaller lever arm. Okay, and so coming here and setting it there we go, bumping it to a height of 80. I'll say ready, 1, 2, 3, go. And wow, that one barely turns. I think that one might even been slower than when we had the weights all the way out at 24 and we were on the big torque radii. Because this is really taking a long time. In fact, what did we get there? 32? Yeah, we're gonna, well, we already tied that on the other one, so we're gonna be way over that one.
Lunchtime? Lunchtime.
All right, so we're at 30 now. And so, coming towards the end here, hitting the ground and stop. All right, so our last piece of data here for today is the time of 47:39. Again, a height of 80 centimeters. And so go ahead and calculate these. And again, as hopefully you'll see, small angular acceleration, medium angular acceleration, and big angular acceleration. And so then you are asked to plot this angular acceleration versus the capital R, the torque radius. And then hopefully you'll see that not only do they get bigger, but they get bigger in a straight line. And that is saying really back here that the torque is proportional to the torque radius. And so that's your third and final graph, and I think that's on page 44. And there aren't any questions this time. So really all you have to do is the graph. So same as before, fill all this in, do the graphs. You can upload it on Canvas, which reminds me, I've got to give you a place to upload all that stuff. I've only put the stuff up to test 1, and so I'll do that as I grade your tests and then think about that, and then we'll start working towards test number 2. So this is our end of our mechanics and the end of week number 3. We're halfway done. I will see you on Monday.